So here's another example with circuits. This one is probably a little bit more realistic in terms of something you might actually have to do because it's got a lot of different types of resistors and they're in a very a semi-complex orientation. So in this case, like the last problem, we want to know how much current is drawn from the battery. We want to know then what's the terminal voltage of the battery, and what's finally going to be a little bit trickier question, what's the current in the 6 ohm resistor. So this time I think we are going to consider the battery as having internal resistance. Remember, most of your problems you're just going to ignore that. A little bit tougher this time. So let's break this down the same way as we did before. So we're going to kind of go into the innermost part of the circuit diagram, and in the innermost part we can kind of see that these two resistors, and by the way, there's no like really wrong way to do this, you're just trying to find the simplest part first. So anyway, I can see that these two resistors, the 8 and 4 ohm, are hooked up in parallel. So I can replace them by saying 1 over their equivalent resistance. Let's say 1, because we're probably going to have to do a lot of different ones. This time is going to be 1 over 8 plus 1 over 4. We could just stick those in the calculator, but you can make a nice common denominator on this one, can't you? Multiply by 2 over 2, and you get eighths is the common denominator, 1 plus 2. So that's 3 over 8, and we reciprocal it to get the equivalent resistance. So the equivalent resistance is going to be 8 thirds, which is about 2.7 with significant figures, 2.7 ohms. Okay, so now we can go to step 2 and replace that with one 2.7 ohm resistor. There we go. You see it now? So now the 2.7 ohm resistor and the 6 ohm resistor are in series. So we can say another equivalent resistance is going to be if we add those up. So that's, you guessed it, 8.7 ohms. That's a 7. So now we can replace those two resistors with an 8.7 ohm resistor. We just keep going like this, so it's not a big deal. So then those two are in parallel, so we'll do them in parallel, right? Make sure you get 1 over, since they're parallel, 1 over 10 plus 1 over 8.7. That one I'm probably going to do with my calculator. That's about 0.21. So the reciprocal of 0.21 is going to be about, what is it, 4.8? Yeah, if you round, it's 4.8. Keeping our significant figures, 2 for all of them. Okay, so those guys can be replaced with one equivalent resistor of 4.8 ohms. There we go. And now remember, this time we were going to consider the battery kind of a more realistic scenario as having some kind of internal resistance. So remember, we're kind of drawing a really big battery here. Let's imagine these are the two terminals of the battery, A and B. And it looks like we've still got another outside resistor too besides that internal resistor in the battery. So, so we've got 3 resistors in series, right? It doesn't matter if like they're on the side or anything. These guys are all hooked up in series. So some of your problems will have like diagonal lines, and then there might be like another guy. If there was like another guy right here, then these 3 would be in series, right? So don't let that stuff freak you out. It's not a big deal. Anyway, so these 3 guys are in series. So the final equivalent resistance, let's just call it equivalent, it's going to be 4.8 plus 5 plus that guy that's inside. We're still going to count him though. So I think that's going to be 10.3 ohms. So that's how much resistance this circuit has in total. So then we go back to Ohm's law, E equals IR, and we can compute the current by taking the voltage in the battery and dividing it by that total resistance that our circuit has. Whoa. So we get a fairly healthy current of 0.87 amps in this problem. So that's part A. What was part B again? What's the terminal voltage of the battery? So remember, in other words, that's like what's the actual voltage between the two terminals of the battery that I've labeled here like A and B. So if we do that, we'll be looking at the voltage drop essentially. So we're going to take that and say that's like the idealized electromotive force of 9 volts produced by the battery minus the current that we found is flowing times that internal resistance. So we're going to get, 9 minus the current we found in the circuit was this much. That's how much is flowing, right? That has nothing to do with this guy, well, except for its little component in there, times 0.5. So I think we get, what is that calculator? 8.6 volts. So you can see there's like a 0.4 voltage drop in this circuit because of that little internal resistance. So most of your problems aren't going to have that, remember, so don't worry about it unless it says so. Okay, so before I start erasing, let's go back up and look. I think we had one last question, and this one I thought was a little bit trickier. Hopefully it won't ask you too many of these. But it says, what is the current in just this 6 ohm resistor up here? So if we want to think about the current just through that 6 ohm resistor, I think let's go back down to where we kind of had it. So we simplified the circuit down to here where we had the 6 ohm in series with this one. So when these are in series, isn't the current through them going to be the same? I think the current through this little setup right here is the same as the current when you've simplified those two in series down here, right? Because of conservation of charge. The voltage across these two is not the same, right? It's going to be like some here and some here. But the current flowing through that branch, since it's just all flowing through it, whatever that current is going to be the same. So in other words, we can kind of go down to this step. I think this is like step 3 out of 4 in this diagram, and worry about it from right here, and that way we won't have to be too overwhelmed. So that's like the easiest way to do it, in other words. So let's think about how much voltage is across this resistor then. And let me get rid of this cat real quick. Okay, so what is the voltage across that resistor? I think the voltage across that resistor is going to be like, let's write it like as V sub 8.7 for that 8.7 ohm resistor. So the voltage across that guy is going to be like the ideal voltage, right? Minus how much that ideal voltage drops between all the other resistors in the situation. So do we have to worry about the 10 ohm resistor? I think not, right? Because like the voltage supplied to these two guys is going to be the same after after it comes out, like in these two parts of the circuit. So the voltage across a parallel construction, you can remember, is always the same. That's really nice to remember, really important. We've done it several times now, but let's say it again. The voltage across parallel is going to be the same. The current through series is going to be the same. That's not true if you mix and match those, though. So anyway, so I don't think we really need to consider this 10 ohm guy because the voltage being supplied to him is going to be the same as the voltage being supplied to him. What we will need to worry about is these other two guys. So there's going to be some kind of voltage drop once the electrons hit those two parts. So it's kind of like they've fallen some amount already once they've gone through these two resistors, if I'm going to use the waterfall analogy, for instance. Okay? So anyway, we're going to go 9 minus that voltage drop. So how much current is flowing in this circuit? We found that that was 0.87 amps, right? So it's going to be minus 0.87 amps times how much resistance those guys have. So total, since they're in series, they're going to have a resistance of 5.5 ohms, right? So we've got the original voltage, and then it's going to drop by this much. IR, right? V equals IR. Okay, then we put that in our calculator and we'll get the voltage that's being supplied, or that I should say not being supplied. You could say current is being supplied. Voltage is being experienced, perhaps. So the voltage being experienced by that resistor is, what is that? I don't have it here. Calculator it, 9 minus 0.87 times 5.5. So I got that was 4.2 215. I guess 4.2 in our significant figures thing. So that's how much voltage is being supplied across that. We know its resistance value, so once again, just use Mr. Ohm. And you get V equals IR. I just like writing it so I don't forget the law. And so we get 4.2 divided by 8.7 equals about 0.48 amps. So I think it makes sense that there's less current flowing through that one, since if we go back up to the very beginning, it's way inside the circuit than there was in the total circuit, which we found was 0.87 amps. Okay, hope you found that useful.